In this video, I want to remind you about the second fundamental theorem of calculus, how it gives us a formula for a definite integral, and most importantly, how we can interpret the answer to a definite integral. So let's start by stating the second fundamental theorem of calculus, which says if we have function f, which is continuous, on the closed interval ab, then the definite integral from a to b of f at x dx is equal to the antiderivative of f at x, which we use capital F to represent that, at b minus capital F at a. And when I say antiderivative, what I mean by that is that capital F, if I differentiate that, I would get lowercase f. So just a note here for you, the relationship between capital F and lowercase f is that if I differentiate capital F, the antiderivative, I get the original function that's in the integrand, lowercase f. And how do we usually interpret the answer to this definite integral? Well, let me draw a continuous function on the interval between a and b. Notice I've placed my upper and lower limits of integration. When we evaluate a definite integral between a and b, usually how we interpret this is that we're finding the area that's bounded by our upper and lower limits of integration, the function, and the x-axis. So we'd be finding this area right in here. But something very important about a definite integral is that it allows for negative areas. Let me show you what I mean by that. If I were to move my upper boundary of integration to here, let's place b here, when I evaluate the definite integral, I will be getting some area that is above the x-axis, and my definite integral will give me that as a positive area. But I would also be getting some area between the curve and the x-axis that is below the x-axis. And my definite integral would interpret that as a negative area. So when I evaluate the definite integral, it'll be adding those positive and negative areas together. And what it gives me is like a net signed area between the curve and the x-axis. So as I take you through a few examples in this video, I'm going to show you how we can interpret the answers to our definite integrals and then also use some integration techniques to be able to find the total unsigned area if that's what we were interested in. So let's start with example 1, where we're simply just evaluating a bunch of definite integrals. And I've got some diagrams to show you what we're actually finding. So part A says to find the definite integral between 1 and 3 of x cubed dx. So I'll mark off my limits of integration at 1 and 3. And we can interpret the answer to this definite integral as the area between this function and the x-axis on that interval. So I'll shade in that area. And because this entire area is above the x-axis, I know I'm going to be getting a positive answer for this definite integral. And now let me show you the notation for how we evaluate this definite integral. The first thing we want to do is find the antiderivative of our integrand. So our integrand is right here, the function we're integrating, it's x cubed. I need to find the antiderivative of that. Or another way of saying that is, what function can I take the derivative of and get x cubed? Well, we can use our power rule, which tells us to increase the exponent by 1 and divide by that new exponent. So that gives me the function x to the 4 over 4. That's the antiderivative of x cubed. And now I want to do that function's value at 3 and then subtract that function's value at 1. So I'm going to do this in two parts. I'm going to start by figuring out the value of this function at 3 and then subtract the value of this function at 1. So let's do the value of the function at 3 first. So I'll sub in 3 for x. It gives me 3 to the 4 over 4. And now I need to subtract the value of the function when x is 1. So that'd be 1 to the 4 over 4. And when I evaluate this, 3 to the 4 is 81. So I've got 81 over 4 minus 1 over 4. That's 80 over 4, which is 20. So there's my final answer. 20 is the value of that definite integral, and we can interpret that as that shaded area you see in the diagram. Let's do part B. Part B, I have the definite integral between negative 1 and 2 of x cubed minus 2x dx. So let me mark off my boundaries of integration again. Notice on this interval, the function is above the x-axis in two parts, but below the x-axis in this green shaded part here. So when I evaluate my definite integral, I'm going to have a couple positive areas and a negative area. And what the definite integral is going to give me, it's going to give me the sum of those signed areas. So the negative area is going to take away a little bit of those positive areas, and I'm going to get a net signed area for this definite integral. So let's get that answer. I need to start once again by finding the antiderivative of my integrand. The antiderivative of x cubed minus 2x, well, the antiderivative of x cubed is x to the 4 over 4. And the antiderivative of 2x would be 2x squared over 2. Well, 2 divided by 2, I could cancel those out. And remember, I'm interested in finding the value of this function at 2, and then subtracting the value of that function when x is negative 1. So let's start by finding the value of this function when x is 2. That would give me 2 to the 4 over 4 minus 2 squared. And now let me subtract the value of this function when x is negative 1. So I would have negative 1 to the 4 over 4 minus negative 1 squared. I want to subtract that whole value. So this gives me 2 to the 4 is 16 over 4 is 4. So I have 4 minus 4 minus, in orange in the square brackets, I've got a quarter minus 1. That's negative 3/4. And if I evaluate this, 4 minus 4 is 0, plus 3/4 is 3/4. So my final answer for this question is 3/4. If I look back at my diagram, those two yellow areas are definitely more than 3/4, but that green area, which is negative, is going to make the total definite integral decrease down to 3/4. Part C, the definite integral between 1 and 2 of 3 over x to the 4 dx. Over that interval, the function is above the x-axis, so the area we would be finding is just this total area between the curve and the x-axis right there, which I know is going to be positive. Before I find the antiderivative of this function, I'm going to rewrite my integrand into a format where it's going to be easier to find its antiderivative. I'm going to write it as 3 times x to the negative 4 dx. And now when I find the antiderivative of 3x to the negative 4, I can just increase its exponent by 1, making it negative 3, divide by that new exponent. And I'll write my limits of integration again, 2 and 1. And I may even want to simplify this. I have a 3 divided by negative 3, that's negative 1. And I'll move that power of x to the denominator, so its exponent is positive. And now I'm interested in the value of that function when x is 2. So that'd be negative 1 over 2 cubed. And I need to subtract the value of this function when x is 1. That's going to give me negative 1 over 8 plus 1, which is 7/8. There's my final answer to that definite integral. Part D, the integral from 0 to 1 of x to the 4/5. Over that interval, once again, the function is completely above the x-axis. So I'm finding the area bounded by the function and the x-axis between 0 and 1, so that yellow area. I know once again I'm going to be getting a positive answer for this. I can start by finding my antiderivative of x to the 4/5 by adding 1 to the exponent, making it 9/5, and then dividing by that new exponent 9/5. Rewrite my limits of integration, 0 and 1. And I'll simplify this a little bit. I'll rewrite this as 5x to the 9/5 all over 9. Let's do the function at an x value of 1 minus this function at an x value of 0. This is just going to give me 5/9 minus 0, which is just 5/9. Let's continue on here. Example 2 says, determine the area of the shaded region on the graph of y equals cos x. For this example, I made the shaded region completely above the x-axis, so we can just use the normal definite integral between 0 and pi over 2 of the function that we have here, which it tells me is the function cos x dx. So I can find the antiderivative of cos x, which is sine x, because I know the derivative of sine is cos. So I can do that antiderivative evaluated at pi over 2 minus the antiderivative evaluated at 0. So I've got sine of pi over 2 minus sine of 0. sine of pi over 2 is 1, and sine of 0 is 0. So I've got 1 minus 0, which is 1. So I know this area right here, its area equals 1. Example 3 specifically says determine the net signed area of the shaded region on the graph of y equals sine x. So this time we have the graph of sine x and we want the net signed area. So not the total area that we see here. We want the net signed area, which is exactly what a definite integral gives. When I do this definite integral, part of it's going to be a positive answer from the portion of it that's going to be above the x-axis, and part of it's going to be negative for the area that's below the x-axis. And it looks like the absolute values of those areas from the diagram are equal to each other. So my net signed area should be 0. Let's see if the definite integral gives us that. So let's find the value of the definite integral between 0 and 2 pi of sine x dx. If I find my antiderivative of sine x, it's actually negative cos x. And my limits of integration are 0 and 2 pi. So I will find the value of negative cos x at 2 pi, and then subtract the value of negative cos x at 0, and that will give me the net signed area. So negative cos x at 2 pi, I'll write that here, negative cos of 2 pi, and then I need to subtract negative cos of 0. Well, cosine of 2 pi is 1, so I've got negative 1, minus negative cos of 0. Well, cos of 0, 0 and 2 pi are coterminal, so cos of 0 is the same as cos of 2 pi. So cos of 0 is also 1, so I once again have negative 1. So I've got negative 1 plus 1, which is 0. My net signed area is 0, and that's because the areas of those two regions have canceled each other out. And I picked this example specifically so you can see that that's how a definite integral works, with those positive and negative areas being added together. But example 4, what if we want the total unsigned area of the shaded region? I noticed the shaded region, part of it is above the x-axis, I'll get a positive area, and part of it is below the x-axis, I'm going to get a negative area. I don't want to interpret any of the areas in this question as negative. I want to find the absolute value of this area and add it to the absolute value of this area. So how can I find the absolute value of all of the areas on this interval? Well, I can find the definite integral between 0 and 2 pi, not of just sine x, but of the absolute value of sine x dx. What's that going to do? It's going to take any of the negative portions of the function, which I've highlighted in green here, and it's going to take that portion of the function and it's going to move it above the x-axis so that we'll be finding a positive area that has an equal absolute value to the negative area. And then I'll be adding that positive area with this positive area, so those two together, which will give me the total unsigned area. So it might be useful if I rewrite the absolute value of sine x, if I rewrite that function into its piecewise equations based on its intervals of when it's positive and negative. And remember, we're only concerned about this function on the interval between 0 and 2 pi for right now. So if I want the absolute value of sine x between 0 and 2 pi, well, I can use the normal sine function whenever it is above the x-axis, which is between 0 and pi. But I would have to multiply the value of sine x by negative 1 if it was below the x-axis, and that is between pi and 2 pi. So I can separate my integral into two different definite integrals. The definite integral between 0 and pi of sine x dx, plus the definite integral between pi and 2 pi of negative sine x dx. Notice the absolute value of sine x on my second interval between pi and 2 pi is equal to the value of negative sine x, because sine is under the x-axis on that interval. So now I just have to evaluate these two definite integrals. It might be worth noting that if we wanted to, we could take that constant factor of negative 1 and move it in front of the definite integral. But I'll just leave it where it is and evaluate it like this. So let me evaluate my first definite integral. I'll do it in green. The antiderivative of sine x is negative cos x, so I want to do negative cos of pi minus negative cos of 0, plus, I'll do my second definite integral in blue. The antiderivative of negative sine x would just be cos x. So I'll do cosine at 2 pi minus cosine at pi. And now let me just evaluate all four of those terms. Cos of pi is negative 1, so I've got negative 1, plus cos of 0 is 1, so I've got 1 plus 1, which is 2, so I know the area of this section is 2. And then my second definite integral, I've got cosine of 2 pi, which is 1, minus cos of pi, which is negative 1. So 1 minus negative 1 is also 2. So the area of this section is also 2. If we just did a normal definite integral, it would tell us that the area was negative 2, but we took its absolute value, so we figured out its area was 2. So I have 2 plus 2, which is 4. The total area of those shaded regions put together is 4. Example 5 says find the area of the region bounded by the graphs of 5x squared plus 2, x equals 0, x equals 2, and y equals 0. Well, let me draw x equals 0, x equals 2, and y equals 0 first. And then it might be a little bit more difficult to graph 5x squared plus 2. I know its y-intercept is 2. I'll just get a rough sketch of this function. When x is 1, its y value would be 7. And when x is 2, it's going to be at 22. So let me shade in the area that we're finding. Notice that total area is above the x-axis. So I can just evaluate the definite integral between 0 and 2 of 5x squared plus 2 dx. So I'm going to need the antiderivative of 5x squared plus 2. That would be 5x cubed over 3 plus 2x. And my limits of integration are 0 and 2. I will evaluate this function at 2 minus the value of the function when x is 0. And when I evaluate this, 2 cubed is 8 times 5 is 40. I have 40 over 3 plus 4, which over 3 is 12, minus, I've got 0 plus 0, so minus nothing. So I have 52 over 3. So that yellow shaded area is 52 over 3 units squared, which is about 17.3. And for example 6, I just noticed I forgot to change my limits of integration for this one. I actually meant for these to be negative 2 and 4. So let me set them to negative 2 and 4. I want to find the total unsigned area between the graphs of y equals x squared plus x minus 2, y equals 0, x equals negative 2, and x equals 4. So let me draw my lines at y equals 0, x equals negative 2, and x equals 4. And I also need a rough sketch of this quadratic function on this interval. I'm going to write this quadratic in factored form. It's x plus 2, x minus 1, so I know its x-intercepts are at negative 2 and 1. Its vertex is going to be at negative 1/2. I don't know how accurate that was, but it'll give me a good idea of what I'm finding here. When I find the total unsigned area, I know that between 0 and 1, I'm going to be getting a negative area. But between 1 and 4, I'm going to be getting an area that's above the x-axis, so I'm going to be getting a positive area. And what I want is to add the absolute value of those areas together. So because I want the absolute values of the areas, I will be doing the definite integral of the absolute value of that quadratic function. So I want the integral between negative 2 and 4 of the absolute value of x squared plus x minus 2 dx. Let me write the piecewise equations of this absolute value function. I can use the positive version of this function, just normal x squared plus x minus 2, if the function is above the x-axis. So that would be on the intervals when x is less than or equal to negative 2, or x is greater than or equal to 1. But I would have to multiply the value of the function by negative 1 if the function had a negative value. And that happens when it's below the x-axis, so that is when x is between negative 2 and 1. All right, now that I know the piecewise equations, I know that between negative 2 and 4, I'm going to have to use two different equations. Between negative 2 and 1, I'm going to have to use negative 1 times the quadratic. But then after 1, so between 1 and 4, I can use the normal quadratic. So let me separate my definite integral into those two definite integrals. The first one from negative 2 to 1 of the negative version of the quadratic, so negative x squared minus x plus 2. And then from 1 to 4, I can use the normal quadratic. So I will evaluate my first definite integral, which I'll highlight in blue and shade in blue here. I'll start by finding the antiderivative of the integrand, which would be negative x cubed over 3 minus x squared over 2 plus 2x. And my limits of integration were negative 2 and 1. So I'll just keep going with this integral. I'll complete that whole integral. Then I'll move over to my second definite integral. I will evaluate this integral at 1 and then subtract the value of that integral at negative 2. So when x is 1, this function would be negative 1 cubed over 3, which is negative a third, minus 1 squared over 2, which is a half, plus 2 times 1, which is 2. And then I need to subtract the value of that function when x is negative 2. That would be 8 thirds minus 4 over 2, so minus 2 minus 4. That gives me 9 over 2, or 4.5. So I know that this area right here is 4.5 units squared. If I'd have done my normal definite integral, it would have given me a negative 4.5, but because I used the absolute value, it then translated the function to be up here to make the area positive. Now let me do my second definite integral, which is going to find me this green shaded region right here. The antiderivative of that function is x cubed over 3 plus x squared over 2 minus 2x. I'll find this function's value when x is 4 and then subtract its value when x is 1. When x is 4, I have 4 cubed over 3, so 64 over 3, plus 4 squared over 2, which is 8, minus 8. And then I have to subtract the function's value when x is 1, which is a third plus a half minus 2. If I evaluate all of that, I get 45 over 2, which is 22.5. So the area of this section is 22.5 units squared. And if I add those two together, I get a total unsigned area of 27 units squared. Jensen Math!